I call this setup here the side-side setup, side-side. When you see these two setups, do you know that when I put another side on that these two triangles are going to be congruent? Well, watch this. When I put another side on this triangle, and I put another side on this triangle, those definitely did not wind up congruent. True? They have two sets of congruent sides, but not three, and even the angles didn't wind up congruent. So those are not congruent triangles. So we would say that a side-side setup would not be a congruence theorem. Let's talk about some setups that are congruence theorems or postulates though. Here's one where I have, again, a side-side setup, but this time the angle is included. They call this an included angle because the two sides connect, and then that angle is already fixed. I'm not allowed to change that angle. I'm not allowed to make these wider or narrower. That has to stay right at that fixed position. So if I'm forced to leave those and I'm not allowed to widen them or narrow those hinges, do I have to, when I put that third side on, would those have to be congruent triangles? And it turns out that they would, because my only choice is just to connect those two endpoints. And if I have to just connect those two endpoints, I don't get to make a choice about how long that third side is. And so these wind up being perfectly congruent triangles. And so one of our new shortcuts is called the side angle side congruence postulate. Here's another little setup, and you'll see that I do have some flexibility this time. The setup here is a little bit special because do you recognize what type of angle that is? That's a right angle. And so this is only going to apply to right triangles. And do you remember what that side of the right triangle is called across from the right angle? This yellow side would be called the, starts with an H, the hypotenuse. And then the two sides of the right triangle that aren't called the hypotenuse are called the two legs. So the setup on these triangles is called the hypotenuse-leg setup, and it has the right triangle included too. So how could I make right triangles out of this? Could I make two different right triangles? Again, I have some flexibility, but then when I put on this other stick, let me see what I can do. I have this short one. When I put on that other stick, I don't have much choice of how to angle it, right? I don't have any choice of how to angle it. I have to point it straight up because I am forced to make this a right triangle. And if I have to point that straight up, I kind of have to bring this hypotenuse to meet it at the top. So on this other triangle, could I use a really long second leg? If I know that I have to point it straight up to make that nice right angle down here, then the hypotenuse wouldn't reach. Do you see what I mean? So the only way that I can make that other leg on my triangle is by making it just the right length so that that hypotenuse can reach perfectly. And so there's only one way to do that. And since there's only one way to do that, it turns out that those triangles will always be congruent to one another. And so when we see a setup like this, we call that the hypotenuse-leg, or the HL congruence theorem. Again, it only works on right triangles. So the first postulate is the side angle side congruence postulate. If two sides and the included angle of one triangle are congruent to two sides and the included angle of a second triangle, then the two triangles are congruent. This would not work if that angle were misplaced. If you see the ticks on these two sides, it has to be this angle that's marked congruent, otherwise it wouldn't work. That's what they mean by the included angle. So we see that RS is marked congruent to UV, RT is marked congruent to UW, And then the included angle would be angle R, marked congruent to angle U. So by the side angle side congruence postulate, using that same order, triangle RST is congruent to triangle UVW. Let's just do a little practice about that whole idea of included angle. If you saw two triangles with their sides marked congruent like this, again, side, side, not enough to prove that our triangles are congruent. But if we had one set of angles marked congruent and it was the set of included angles here, then we could say the triangles are congruent. My question is, which of the three angles would be the included angles? What we'd want to think about is, where do those two marked sides connect to each other? Do you see how those two sides connect at this vertex? And these two sides connect at this vertex. So those 2 points are where our included angle is located. So if we knew that this angle right here was congruent to this angle right here, that would be a side angle side setup, and that's all we would have to know that everything else was congruent to each other. Then we could know that the third side was congruent to the third side, and the other angle was congruent to the other angle, and the other angle was congruent to the other angle. We would know that everything was congruent because these triangles would be congruent by the side angle side congruence postulate. Let's try a proof. I told you these are going to get fun this chapter. So we are given some congruent sides, which is always nice. I'm going to mark those on the picture as I mark them on my proof. So it tells me that JN is congruent to LN. That's a set of sides. It says that KN, I'll use double ticks this time, is congruent to MN, double ticks, and that's another set of sides. And I'm going to need three things to prove that these triangles are congruent. Now there's not really a good reason that I could mark that JK is congruent to LM. They totally look congruent, but I don't have a good reason to back it up, so I'm not going to be able to say that. But how about our new theorem, our new postulate that says the whole thing about the included angle? Can you see where the included angle would be for our two sides? See how they join up at point N? Is there any way that we could talk about that included angle? Any way that we could say that angle N for this triangle and angle N for this triangle are congruent to each other? Now we can't call them both angle N because technically they're different angles, right? So maybe I'll call the one on the left angle JNK and the one on the right angle LNM. Now since they're not the same angle, it's not reflexive because it's not angle N congruent to angle N. They're actually different angles. Can you tell me what type of angles they are? Some of you might have this already. What type of angles are formed by a crisscross like that? I bet you got it. Those are vertical angles. The reason those are congruent is the vertical angles congruence theorem. In fact, I refer to these diagrams as bow tie triangles a lot. If you ever see a bow tie triangle, you're probably going to use the vertical angles congruence theorem because vertical angles are always formed in the center of those bow ties. All right, you guys, we have a set of angles that is marked congruent. Now you'll notice that the order that I write these in doesn't make a big difference. The order that matters is the order on the picture. I definitely don't have an SSA congruence postulate. But that's not the order I'm looking at up on the picture, right? I'm talking about my two sides and their included angle. I'm talking about a side and the angle that's between them. That's more of a side angle side setup. Can you see that? So I'm ready to use the side angle side congruence postulate. And what does the side angle side congruence postulate tell me? It tells me, it's right in the name, that the triangles are congruent. That's how simple some of these proofs can be. Our other theorem of the day is called the hypotenuse-leg congruence theorem. Again, it only works for right triangles because of the hypotenuse, right? If the hypotenuse and a leg of a right triangle are congruent to the hypotenuse and a leg of a second triangle, then the two triangles are congruent. Our other two triangle congruence postulates have 3 letters: side, 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 angle, side, and sometimes I'll even write this one as hypotenuse leg, and the fact that it has to be a right triangle, that's important too. So sometimes you'll hear me call this the HLR congruence theorem, because you have to make sure that you have a right triangle if you want to be calling something a hypotenuse. Here's a little picture of some definite right triangles. Do you see that nice little right angle in there? We've got perpendicular lines, and anytime you're given perpendicular lines, we know that we've got some right triangles going on there, right? If we have perpendicular lines, we can say that all of those angles are right angles. So we've got 2 right triangles. In addition, it looks like we're given a midpoint, so I could say that this and this are congruent to one another. And what do we call that when the 2 triangles are sharing a side? Can't we put tick marks on that shared side because side AB is congruent to side AB or whatever? They're sharing a side using the reflexive property. Now, did you notice that I didn't put any markings on this side? Because there wasn't really anything to tell me that that side of the triangles were congruent. What's that side of a right triangle called? That's called the hypotenuse. So in this figure, I don't have the hypotenuses marked congruent. In fact, what I have here is I have 2 legs and then these angles figured out. What this actually is a side, and a couple of angles that happen to be right angles. This is actually a side angle side setup. So just because you see a right angle doesn't mean we're automatically going to hypotenuse leg. You have to be really careful. The only time we'd be using hypotenuse leg is when we see the H's marked congruent, the hypotenuses, one of the legs marked congruent, doesn't matter which leg, and the fact that we have right angles. That would definitely be an HL setup. So once again, just because you have right triangles doesn't mean it's auto hypotenuse leg. You have to make sure you're looking at an actual hypotenuse and a leg marked congruent. This one just has a ton of O givens. Let's see what we can do with all of that. It looks like AC is already marked congruent to EC, and that is definitely a set of sides on my triangles. I have AB perpendicular to BD. Can't I say that this is a little right angle then? I think I'm going to throw that in my proof. Angle B is a right angle because of the perpendicular, right? Definition of perpendicular. I'm just going to check that off. I used that one. ED is also perpendicular to BD, so why don't we say that that angle D over there is also a right angle? Then what can we do with that bisector? That's got to be something good, right? It looks like it's a segment bisector, right? We don't have any angles in there. Segment AC is a bisector of segment BD, so I'm going to try to use definition of a segment bisector. And let's look at the picture. It's saying that this AC is a bisector of BD. That just means that it's cutting BD in half right at this point C. Kind of the same idea as C being a midpoint. So that just tells me that I know that BC is congruent to CD. And I've got myself another set of sides. Okay, so question, when I look back at this picture, am I talking an HL or am I talking a side angle side? What kind of setup do I have up there? So I definitely have the right angles. So this is a candidate for hypotenuse leg. Do I have the hypotenuses marked congruent? Which side is the hypotenuse? The hypotenuse is the one that's across from the right angle. That was the ones that were given to me. Those are the hypotenuses. And I have another set of sides that are marked congruent. Those are considered legs. These other guys would be considered legs too. But this is totally a hypotenuse leg setup. So maybe I was too quick to call AC, this first one, when I said that, oh, I have a set of sides. Side AC congruent to side EC, that was more of a set of hypotenuses that were congruent. And when I marked BC congruent to CD, that was my set of legs that were congruent. And when I said that B and D were right angles, that's where I was showing that I had my right triangles. And now I can see that I have the 3 criteria to say that I can use the HL congruence theorem. And what does the HL congruence theorem tell me? That the triangles are congruent. It's update time. Side angle side congruence postulate. HL congruence theorem. And then if you flip over, let's label a diagram for each of those. Side angle side, we know that we're going to tick one set of sides. We'll tick another set of sides. And then let's think about this. What set of angles would we need to mark congruent? Remember, it's the set of angles that is included between those 2 sides. So it would have to be the one where those 2 sides join together. So that would be the side angle side setup that proves that those 2 triangles are congruent to each other. The next set on there, let's mark an HL. I think the closest on these to right angles are probably these top angles. Let's mark those as our right angles. And if those top angles are the right angles, where would the hypotenuse be? The hypotenuse is always across from the right angle. So the hypotenuse would be right here. If you're worried about remembering that, maybe you want to label that with a little h. So hypotenuse-leg, totally up to you which other side you call your leg, but we would need just one other side marked congruent in order to call that a hypotenuse-leg setup to prove that those triangles are congruent.